reason and has certain function. There's a very peculiar reason why it is shaped the way it is and has that weird sort of sitting on that weird sort of sail-looking thing and everything. So there are reasons for it.
Sure, of course. All right. So for people who haven't kept up on the James Webb telescope, that, as you know, all the billing has been saying, it's going to look back at the origins of the universe. Which, if you could, some point today, explain to us what they mean when they say that kind of stuff. You know, when the
sure
when they get at that. But this has been really coming for a long time. A lot of people paying attention since, you know, late December, maybe Christmas morning when the thing launched, you know?
Yeah.
But this has been what decades in the making?
Decades. In fact, there was probably about I didn't keep up after a while, but there's at least a decade's worth of delay in there too. The original plan was for it to launch sometime in maybe 2010, something like that. Okay. So there's been a lot of delays.
Well, Paul, one of the great things about your tutelage here on the podcast is that you know how to take it slow for those of us who don't really understand this stuff. So how is it that a space telescope like this with these hexagon shaped, panels can draw light in and then allow astronomers to see into the past? Can you just describe that?
That if you're looking at the picture, basically the big gold, strange shaped gold thing there made up of all those hexagons is a mirror. Okay. All it does is take light and reflects it back onto that little device there at the end of those three long legs.
A little round disc.
Focuses the light there. And it doesn't really so much soak up the light as it does sort of just get in the way of the light. And the light just bounces off and gets received by that little device there. So basically, it's just a big mirror is what you're looking at. The gold part of it is just a big mirror.
Okay.
But the other question about how does it look back in time? Well, it's to the beginning of the universe, right? That's a time statement.
Yeah.
So what this basically means is this, if you're standing on one side of a room and your friend's on the other side and you wave to your friend sees you wave a few nanoseconds after you actually wave, because it takes a few billionths of a second for light to make it across the room. So whatever you see anything happen, you're seeing it happen a little bit later than it really happened, even inside of a room. But a billionth of a second doesn't make a difference.
Mm-hmm.
Right? Doesn't make a difference. You can't notice that. The moon is about maybe a couple seconds away. So if you were staring at the moon and the moon were to explode, you would see it explode 2 seconds after it actually explodes. So there'd be 2 full seconds between the time the moon blew up and you saw it blow up. Because the light takes 2 seconds to get to us from the moon.
Which, for those of us that could have any anxiety about, did the moon just explode?
Away. So if the sun were to explode, we would carry on, same as normal, for 8 minutes and 19 seconds.
Oh my gosh.
We wouldn't know that it blew up until 8 minutes and 19 seconds after it did. And so the further away we go in space, the further back in time we're looking. The nearest stars are several light years away. So we're seeing the nearest stars as they appeared 4, 6, 10 years ago. And if they were to blow up or be eaten by a big dragon, we wouldn't know it for 4 years or 6 years or 8 years. The star would continue to look the same as it ever did for the next 4 years, for example, until we finally saw the big dragon eat it 4 years after the dragon actually ate it.
So this
telescope looks not years away, not millions of light years away, but billions of light years away, billions of years back into the past.
I see. Okay. So I'm not sure if you can hear me or not, but I think maybe, Paul, you're having a little problem hearing me. Can you hear me right now? I think there's a little glitch here, Dan. Do you think? Yeah, now he's going to fuss with his. We were folks who were paying attention. We were coming on here earlier. Paul was having a little bit of trouble with his with him hearing us. Can you hear me now?
I can hear you now. I'm so sorry.
That's okay. So a few seconds ago, I said something, and now it's traveling through the world and getting to you. So that's always it's a delay that you always expect, because that's how physics works. Okay, so here's the part, Paul, that kind of baffles my mind. These illustrate, like, I think, okay, if the moon exploded, the light waves would leave the moon, and it would take whatever number of seconds to get here to Earth for us to see it.
Yeah.
But then those light waves sort of just would, here's what confuses me. It feels to me like the light waves then would just keep going. And if somebody was near the Earth and they looked 20 minutes from now toward the moon would then be gone. There wouldn't still be light waves coming. So how does a telescope like this, where these light waves that show the start of the universe, why are they not already past where the telescope currently is? Like, why did those? I guess it feels like the way it's being described is that the light waves sort of keep coming, or the light waves are going away from the telescope.
Oh, I see.
Do you see my dilemma?
You're saying that the light should have already passed.
Yeah, that's what's confusing to me. Yeah. So if I turn this light on in front of me, and it comes on and then it shines on my face, and then I shut the light off and it's not on anymore, I'm not going to see those light waves. It's not like I could run way back across the room.
Right, but think about looking out across the sky.
Okay,
and you're looking at, say, you see the moon, you see Jupiter, you see distant stars, you see galaxies.
Okay.
You're seeing all these things at the same time. They're all entering your eye at the same time. But the times you're seeing them are all different. I mean, you were seeing, you're not seeing them as they are now. You're seeing them as they were. And the further back you go, the further back you're seeing it as it was.
Wow. Okay. So this telescope, then, the reason it's so important for this is it can see further.
It can see further for at least two reasons. It can see further than Hubble. The first reason, and it's really important, is that it is bigger. Okay. Telescopes are one of these situations where size really matters.
Because of the amount of light that it takes in? Is that the
telescope is enormous and much bigger than Hubble.
Is the reason because the more light can come in off of those mirrors? Is that what it's all about?
Yep. It's like having if it's raining outside and you want and your goal is to collect water. You want the bigger the bucket, the more water you get. It's that simple.
Sure. Yeah.
It's that simple. The more light we get, the better our images are. The more light we get, the higher the resolution and the fainter things we can see. So that's the first reason why it's has better vision than Hubble. That's the first reason.
What are the other reasons that it's better?
The second reason is that it doesn't actually operate in what we call visible light. It doesn't see the light that you and I can see.
Yeah. Okay. This is going to help. All right. What light is it? Is it picking up?
It's picking up infrared light. Okay, which is light that has a little bit longer wavelength than our color red.
Okay.
That's why it's called infrared. So it's a little bit longer. It's normal light. There's nothing mysterious about it. It's just that our eyes are not tuned to detect it. It's very real. We experience infrared light as warmth or heat.
Yes. Yeah, I have an infrared sauna that heats me up.
You're lucky. You have a sauna in your house?
I do. I have an infrared sauna in my house, so it doesn't heat up. To your point, what makes an infrared sauna magical for someone's house is that it doesn't heat the air. It heats the objects in the sauna. So the air gets a little...
The air gets eventually would get to be that same temperature over time.
Yeah, the air gets a little bit warm, but unlike sort of a moist air sauna where the air gets real hot and you walk into the sauna, we like to describe it like the difference between humid air outside and the warmth of the sun, where you could actually feel cold air, but the sun feels warm because it's warm. So it's that.
Well, that's a useful illustration. I mean, if we turn the Webb Space Telescope onto your house, Doug.
Mm-hmm.
That room would appear very bright.
Okay. All right.
It would detect that room it would be the brightest thing in your house. So it detects infrared light, and there's more infrared light in the universe than any other kind of light.
How do we know that? How do
photons or particles of light? There are more infrared photons in the universe than any other kind of visible light or X-ray light or ultraviolet light. There's just a whole lot of infrared photons out there.
Okay. And
that's another reason why it sees better, because there's more light of the kind that it detects.
I see. There's just more of that infrared light moving around.
Sure if my connection is working here or not.
Maybe just unplug all that and go straight out of the Paul, maybe just unplug all that and go straight out of the computer. Maybe that would.
Yeah, I think I'll do that. Give me
your sound. Your sound might be a little different. Well, hey folks, if you have any questions and you're in the chat, no, Julio wants to talk about infrared sauna. Hey, I'd be glad to. Julio, message me separately. I'll tell you what I know about infrared saunas from our purchase experience. But if you have questions about how this all works, the thing I love talking to Paul is just trying to get my head around like how the science works, because I have these little blockages of assumptions about how I think the universe functions. And even blockages. Paul, when you just said infrared is a longer light wave than the light wave of red color, that's why it's called infrared. That just opens up a whole Pandora's box of understanding. Like, wow. So that's where that comes from. What is, so light waves length, that has something to do with why our eyes can't see certain.
Yeah. Can you hear me now?
Yeah, we got you. Sounds great.
Great. Fantastic. Yeah. It's just that so happens that our eyes, human eyes, are tuned to a certain range of what we call wavelengths.
Okay.
Light of it's a pretty narrow window actually of wavelengths are our eyes sensitive to. It's kind of like hearing, you've heard of dog whistles, right? I mean, actual ones and political ones, right?
Yes.
But the actual dog whistles it's real sound, but our ears aren't tuned to hear it. It's outside the range that our ears are sensitive to. Same thing with infrared light. It's real light. It's just that our eyes can't detect it. Now, if you put on some infrared goggles, the heat sensitive goggles, then you can see you can see bodies at night in the dark because they emit infrared light.
Got it. Okay. So why is it that seeing infrared helps to see further back in time as to what took place previously?
Yeah, two reasons for that. One is that, like I said before, there's just a whole ton of infrared light out there. There's just more of it. Not only that, but infrared light travels through stuff that visible light does not, like dust. There's a whole lot of dust and gas in the universe, and visible light tends to get scattered by that.
Wow.
But infrared light will travel straight through it. So we can see through stuff. We can see through some stuff in the universe that we can't see through with visible light. So it's like your windows. It's like windows are transparent to visible light. That's why we use them. But they are opaque to infrared light. Different wavelengths of light travel through different things.
Oh yeah. So like if you're sitting by a window and you can see the sun and the sun looks nice and bright, you don't feel the warmth of the infrared rays
Right.
from the sun. But if you go outside,
Right.
soon you start to feel it because the window blocks the infrared waves.
Right. Right. Now, if you're
How
sitting
does
in your
that
car,
work?
well, if suppose you're sitting in your car in the
Yeah.
winter. Now, you know about this.
I
You
do.
park your car out in a sunny, cold winter day. It's 20 degrees outside. You get in your car and it's 50. And
Yeah.
it feels great.
That's right.
You know, what happens there is the visible light from the sun passes through your window and gets absorbed by your seats in your car, the upholstery, whatever. And that upholstery ends up re-radiating that energy back out as infrared light.
Oh.
And that gets trapped in your car. It's the greenhouse effect. Same thing happens with our atmosphere with global warming. It's exactly the same thing. Visible light strikes the Earth's surface. The Earth's surface re-radiates it back out as infrared light. And that infrared light gets trapped by the Earth's atmosphere.
Because all heat is infrared.
That's all it is.
Or infrared rays.
It's just the way we physiologically experience infrared light. We call it heat. Yeah.
So there's nothing actually. The protons are not, electrons are not moving faster, heating something up in a physical way. Our human skin and body just feels it as infrared?
The light hits our skin and makes the electrons and so forth in our skin oscillate faster.
Makes those oscillate. I see.
And that's we feel that and we go, oh, it's warm.
As opposed to the air getting warmer because of the humidity in the air or something.
Right. Right. It's all the same thing. The air does get warmer as well. And that's why our temperature keeps going up and our ocean water expands and rises and everything else.
See, this is where that, energy equals mass, times the speed of light. That thing, that energy and light are the same thing.
Yeah.
This whole notion that sort of rolls around in our world, and we just sort of assume, actually becomes really explanatory and functional for people that are looking back in the universe. So they're okay when they're looking now back in through the James Webb Telescope, and they're looking back into. They're finding light waves that were let's see if I have this right. That were generated when the universe started its expansion. Is that right? Those are the light waves.
Shortly after, several million years after the Big Bang.
And those light waves are still moving somewhere. Like they haven't stopped.
Right. They're coming from every direction. Yes. They're coming from every direction. And they're always visible.
They're always okay. Can you just help me understand that one? Is all light always? Are the light waves always moving? Like they'll never run out? I guess again, I think about them more like a baseball that someone throws. Like that it starts.
So let me get your question right. Your picture is that the universe already got started.
Yep.
And that light should have passed over us a long time ago.
That's right.
So we wouldn't see it anymore.
Yeah, I guess I'm thinking of like, say the moon exploded, then those light waves would pass by, and you look at the moon and you see, oh, here come there's the explosion of the moon, and then 3 days later you look back to where the moon was. You're not going to keep seeing that happening over and over.
Oh, okay.
Those light waves have moved by this spot in this place in time, or this place in.
I get what you're saying. Let me see if I can come up with a good.
Is it such a bad concept that it's even hard to explain?
No. Actually, it's a really good question, and I'm trying to put the answer into the right. It's actually a really good question, and the answer is that this
is so great.
Let me put it this way. The event has already happened, okay, but I need to come back to this. I'm getting tripped up. There's something that I'm missing.
Oh, I empathize deeply with that.
And I don't want to.
Yeah, there's something about my brain.
Made on the point too long, but I will come back to it and
all right.
and give you a decent explanation.
Well, okay, all right. So, and I think somehow I've got something caught in my head here about sort of how light works. That's always perplexed me when they say we can now look at light waves further away and see them. So it makes me think they're moving.
What do you mean by seeing them? I mean, from sources further away?
Yeah, well, when they say, hey, this telescope is going to allow us to look further away in space, so then we will see the origins of the universe.
Right, because
that's what I understand the explanation to be of how this works.
So, because the further back you look, the further back in time you are looking. I mean, I think you see. Do you see that, how that works? The further away a thing is located, the longer ago the light left that object.
Yeah, no, I get that. Yeah, so and I guess it's sort of the position of things that trips me up. So I think, okay, where the universe banged into creation, all the compounds exploded, and then the Earth is flung however many billions of miles away from that origin spot.
Okay.
Is that right?
Yeah. No, I see what the issue is.
Okay. And then are we looking back at that origin spot? Because when
no, there is no origin spot.
That's what I thought. Okay, because then,
or rather, every spot is the origin spot.
That's the one part of my brain that thinks that. But then this other side is like, well, if you look back further, and maybe it's just the way this language gets used, whether this kind of time space language, like if you look back further,
okay.
If you look away further, you're looking back.
Okay, this one I do have.
We started there and we came here.
Here's the situation. The popular view of, say, the Big Bang is that there was all this empty space kind of just sitting around, space as we know it, X, Y, Z, sitting around with nothing happening, just nothing happening. And then all of a sudden at some point, some location, X, Y, Z, this thing exploded and has been rushing out into all that space that already existed.
Okay.
That's not right, because the view of the Big Bang that astronomers carry around in their heads is not like that. It is this. All of the space that we know was also wrapped up in that Big Bang.
Okay.
So think of it this way. Think of a balloon expanding. Suppose you're like a little bug stuck on the surface of this balloon. Okay.
Yep.
And, inside and outside the balloon don't have any meaning to you. You were stuck on the surface of that balloon. So you're a two-dimensional creature on the surface of this balloon. Okay. And so you're stuck to the surface. You're stuck within the surface of this thing. And now imagine the balloon starting from a point and expanding from that point.
Okay.
Every point in your space, every point on the surface of that balloon was located at the same point originally.
I see.
And it's all expanding, and the expansion of space is carrying the galaxies and everything along with it.
Okay.
So space itself was created at the Big Bang and is stretching out, carrying everything with it.
Okay, so that's great. So everything is captured up in that,
right?
Whatever it is that it expands and opens.
Right. So every point in space was located at the same point when it started.
Yep. So that all opens up. But now we can say, well, rays from the sun are going to now travel the distance to get to the Earth. Mm-hmm. So now there's some kind of travel distance that's happening with light waves.
Yep.
Okay. So then when I hear people say this telescope is going to look back, Or when we talked about it earlier and you were saying, well, it's like if you looked, at the moon and it's going to take time for those light waves to get here. So some matter of seconds, and then 8 minutes and 19 seconds for the sun's explosion, which I'm still worried happened 7 minutes ago and we just don't know yet. Yeah. So I've got that anxiety hanging over my head. So those things are now a point, and there's light waves that are now traveling to where we are. Mm-hmm. When this telescope gets into this space, the spot in space where it can sit stable, and starts looking in a particular direction.
Yep.
Why does it, if everything is sort of equal, why does it need to look further away to see the origins? If every spot is the same spot of the expansion, why this language about look further away from where the telescope is in order to see the beginning of things? Because that starts to feel like it creates a different story of things started there and are traveling here.
Oh. Give me the alternative. What it...
How come looking further away from the spot where the telescope is has different information than what's 2 feet away from the telescope?
Because we're looking at things that happened earlier.
Because they're further away?
It doesn't matter earlier? It doesn't matter where we put the telescope.
Okay.
The universe would look basically the same from any point in the universe.
So why don't we just have that telescope here? Like, why do we have to launch it up and get it to land in that sweet little spot where it doesn't move because of gravitational pull? Like, why did it have to go out there?
That's just a technical issue. It's a convenient place to put it.
But why don't we just have it here on top of a mountain on Earth?
Because of the atmosphere.
Our atmosphere is the problem.
Yeah, and also because it's got to basically avoid looking at the sun. You cannot let it. It's way too sensitive. If you turn it anywhere toward the sun, it would blow its circuits basically.
I see. It's got to get away from our sun so that it's not picking up all that.
And it's got to get it's got to get way above our atmosphere, basically. Because our atmosphere blocks so much light. So it doesn't matter where in the universe we put it. The universe would look qualitatively the same from any point within the universe. There's not a special point. We're not at a special place in the universe.
I see. But it feels like they're really directing this thing, like they really wanted it to land in a certain spot. I get it. So it will stay there for gravitational pull. And then they want it to be directed in a certain direction.
Yeah.
And that's just so that all the mirrors line up. Like it's not, could face any particular direction.
You know, that big weird shield thing, that big sort of silvery looking sail that it's sitting on top of there. Yeah. That's a sun shield.
Okay.
It basically, the bottom of that thing in the picture will be always pointing toward the sun.
Okay.
And the bottom of that sail in the picture here is going to be extremely hot, and the mirror side of the telescope will be extremely cool.
Got it. Okay.
So basically, that big silver thing is a way of blocking the telescope itself, the gold thing, from the sunlight, and it will and the bottom of that silver shield will always be facing toward the sun.
I'm just going to try this one more time.
Okay.
Straighten up my mind, see if you can help me, and maybe Ryan Phipps will have to make a meditation podcast for me to get my head right around this. So if there are no special places and just needs to block out the radiation of the sun and still be in communication with the earth, and all those things have to sort of be right.
Yep.
If the Big Bang's origin is not a fixed point somewhere, didn't happen in a spot.
It happened everywhere.
It happened everywhere. Then are we saying that the light waves are sort of moving away from this telescope, and the telescope can see them further than the naked eye could or than Hubble could?
Yeah, the light waves are moving towards the telescope, not away from it.
Moving towards it.
Well, actually, they're moving in every direction.
Every
But
direction.
the mirror only picks up those that are moving towards it.
So, okay, that's getting helpful. So it's bringing in a lot.
So the light from the beginning of the universe is coming down on this telescope from every direction equally.
Okay. I guess that's what's got my head spinning around as we say it's going to look further away back in time. Those two words, further away and back in time. But then you're saying, no, the light waves are actually coming toward.
Yeah, and I think this is actually the resolution of that question that I had a trouble with a moment ago.
Yep.
The truth is that the origin of the universe happened, the Big Bang, happened everywhere.
Yeah.
Okay, including where we're sitting. Okay, it happened everywhere.
Yeah.
So the light from the local Big Bang is already gone.
Okay. It's helpful.
Okay, it's already gone. But if it happened everywhere, then there's got to be, then we can look in any direction. If only we look far enough, we will find the distance and find the time at which the Big Bang happened. In other words, unlike the moon, which explodes in a certain point and from a certain direction.
Yeah, got it.
The Big Bang happened everywhere at the same time. So the local light is already gone. But if we go a little further out, we're looking a little further back in time, and the Big Bang light's also gone from that point, but more recently. Got me? So if we keep going back and back and back and back and back, eventually, because it happened everywhere, we will hit that distance that corresponds to the time at which it happened.
Yeah. Okay. So there we go. Okay. That's helpful. Because I guess that's it. Oh man. How long was that? How long were we after that little thing? I hope other people enjoyed that little journey too.
The key comes when you realize that the Big Bang happened everywhere. That's the difference between the Big Bang and the moon.
And that the local light is gone, which if people are watching online right now, for some reason, literally the light behind me went out when we were saying that. I can't explain it. It's never happened before. It's just happened now. So I guess because here, the thing that gets me about telescopes is that when I think about a normal telescope, you look through, there's an object you're looking at, you look through it with your eye, and you then can see further than what your eye can see. This feels like it's a different kind of telescope than an optical telescope or something. Like it's not just zooming in on a further away object, or
it really is the same thing. So it's a lot more high tech, a lot more challenges. It's a much more subtle thing, but the basic idea is exactly the same as our eyes in our backyard telescope. It is no different in essence from that. It's more of a challenge technologically, but we're basically collecting light in a great big eyeball. That's all we're doing.
And this light so everything else I look at through a telescope is light shining on something, and then I'm seeing some sort of light emitting or matter or something.
It works the same as your eye. The light comes in and hits a photosensitive surface.
So in that little disc that's on the front of the telescope, so the light comes in, hits the mirrors, and then gets directed into that, whatever that receiver is.
That operates like your retina, basically.
And that then sends what to scientists? What do they get from that? Like if I push the analogy too far, I'm like, well, if I look through a telescope, I see, my brain conjures up the object that I'm looking at, right?
Right. It sends a digital image. It just sends a picture. It's just a big picture making machine.
Huh. And what do light waves look like? So if they're not looking at a planet, are they? Looking at
They could, but I don't think that James Webb will be looking at any planets It probably will look at some planets in our own solar system. Sure.
Okay. What more often will it be looking at? A whole variety of things that are
it'll be looking.
Is the origin of the universe part just one thing that this telescope is going to do? Like it's going to do a whole lot of different things?
In my mind, there's like 2 or 3 things it's going to do. One is it's going to look back, to the origins of the universe, shortly after the Big Bang. It's going to do that. It's going to look at stars called brown dwarfs. I like that for a name, huh? Brown dwarfs.
I just did.
These are basically objects that fall somewhere between planets and stars.
Really?
They're odd little objects. Yeah. Jupiter's kind of like a small brown dwarf.
Huh.
Yeah. And these objects exist out there. They're basically stars that weren't massive enough to start fusing hydrogen and become stars. They're kind of like failed stars.
God, feels like my life. Yeah, sort of.
I know.
I have a whole new idea for how to describe
failed stars. So,
I'm a brown dwarf of human experience.
So they're very bright in the infrared, so they show up in the infrared. So they're going to do that. And third thing that Webb's going to do is look at other solar systems in formation.
Okay. Wow.
Solar systems like our own, but in the early stages of formation.
How will they know that's what they're seeing? Like when they look and see blurry images or whatever, or clear images, how do they know, oh, that's a galaxy in formation?
Solar system in formation. Well, there's certain things that you can tell. Basically, what they're looking for is a disk of gas and dust with really bright things inside of it.
Wow.
Because our solar system, 5 billion years ago was. Think of it like you go to the pizza place and the dude takes the pizza dough and throws it up and it flattens out in this disk. So something like that, gas and dust, a big disk of gas and dust with a number of little bright points in it. Which are planets in formation, and with a star in the center of the whole thing. The nice thing about the infrared is that it can sort of look through that gas and dust to see the planets, the planets that are hotter than the surrounding material.
So we have a pretty good idea of what things would look like that description right there.
Oh yeah. We've gotten plenty of pictures of it with Hubble, but we're going to see these things in unprecedented resolution with Webb.
Do we expect that scientists will start to see things that they don't know how to explain, and the next 30, 50 years are going to be built for some people around explaining what we're seeing? Or do you think
that is the hope?
That's the hope. So the hope is to say, let's not just see the things that we know how they work, but let's bend our minds into we don't know what this is and what this is all about. And
there are some very large questions in cosmology. I mean, in some senses, cosmology is in as big of a mess as it was before Copernicus. There's big questions that we don't know the answer to, and maybe this will lead us down some of those paths, but also open up new questions.
Okay, there's a couple of questions that people are putting in the comments that have been happening over time.
Sure.
Can you pop into a few of these? Julio asked, can infrared be used instead of X-rays? Do you know, is that a thing? Can infrared rays?
For what purpose?
Like looking inside the body, I guess.
No, infrared will just be absorbed right on the surface of our bodies, and we'll feel nice and warm. But the thing about X-rays is that they've got a lot of energy, and they burn right through. They go right through our soft organs.
Okay.
But they get absorbed by our bones,
and that's why you see the bone.
So you get a bone shadow, basically.
That sounds like the name of a band. We should start right there.
Bone shadow.
That
is definitely the name of a band.
All right. Jim says, are we going to see past events on Earth with this telescope visually?
Past events on Earth? No.
It's not going to point at Earth at all.
No.
not gonna take this in.
But
Ryan,
that reminds me of a science fiction story I read once, and I can't remember. I was like a teenager or something,
yeah.
about some big mirror out in space, and we could look in the mirror and see things that happened on the Earth, thousands of years earlier, because the light bounced off the mirror and reflected back to the Earth. But it took 1,000 years to do that. So interesting thought. But the answer
God, that's awesome. Yeah. See, that's the kind of, that's that space-time warping, bending over, and time is not what we think. How much does the fact that time is not what how we sort of think about it, just in a linear way, that space and time are the same thing? Is that part of this seeing and looking in the past and distance business that's got my head so spun around?
There is one nice effect that I haven't mentioned yet that is going to be Webb is going to be useful with, is that this if a light wave is emitted by a star and it's visible, so let's say it's a green photon, and then let's say it's a red photon. It's a red.
Makes no difference to me, but yes.
Yeah. Well, it makes a difference to me. Let's say it's red.
I know it does.
Okay, yeah. The universe is expanding, right?
Right.
Well, as that light wave travels and the universe expands, the light wave expands also. So it can get expanded from the visible into the infrared as it travels. If it travels long enough, it will expand with the universe. It's called the Cosmological Redshift. How's that for a fun title? But basically,
that's the name of our album from the Bone Shadows, the Cosmological Redshift.
So the Webb will be able to see light that used to be visible.
That is helping so much. Okay, so this light that's now moving away in an expanding universe can now be picked up because it's also expanding and turning into a different kind of wowzer. Right. Are you sure all this is happening? This isn't just a big. Are you sure?
I'm not making this up. And also on the other end, ultraviolet light becomes visible, and we could, Hubble could detect light that was originally ultraviolet because it started off in, beyond the blue side of the spectrum and got shifted into the visible part of the spectrum as it traveled. Weird.
So I didn't know that there was infragreen. Is that what you're saying? There's infrared and there's infragreen?
No. I'm saying there's infrared, which is wavelengths that are longer than red, and our eyes can't detect them. There's also ultraviolet, which is light waves that are too short for our eyes to see.
When you were saying the red proton and the green proton, that doesn't also translate into there's wavelengths longer than green and longer than blue or something. Only infrared, only red is the wavelength that's
long. Yeah. So think of it. Think of the visible part of the spectrum like the middle octave on the piano, like the middle eight keys of the piano. Okay.
Let's pretend I know that.
Okay, so there's, in other words, take the middle 8 keys of the piano, the middle 8 white keys of the piano. Okay. You know what a piano is, right, Doug?
I've seen these. Yes.
Yeah.
Not really sure how it all lays out. It's like my wife's emotions. I know they're there. Just don't know how to make any sense out of her.
Okay, so the point is that if you take the middle 8 keys of the piano, middle 8 white keys of the piano, okay, imagine that's all you could hear.
Okay.
Outside of that, somebody sitting there playing the piano, they're playing notes higher than you can hear, playing notes lower than you can hear. They're real notes, but your ears can't hear them. Okay, so the low notes there are it's like the red wave that you can hear. The lowest note that you can hear is a red wavelength. All the notes below that are perfectly good notes, but they're too long for you to hear. That's the infrared.
That's infrared stuff.
And the notes that are too high for you to hear are the ultraviolet.
And when we say the infrared, I feel like when I hear ultraviolet, I think about a whole bunch of colors, ultraviolet colors. And when I hear infrared, I think of one.
No, they're even applying the word color is not really right because we can't see them. So but having the words red and violet in there kind of make you think they're actually colors, but all that means is below the red and above the violet.
So it's using red and violet as a reference point and saying
Exactly.
it's longer or shorter than those. Okay. Well,
That's
hey,
all it is.
This is helpful. All right. So back to a couple of these things. Kevin Stuck says, what caused that initial Big Bang? Is that something they're going to try to explore with the James Webb?
Yeah, that's not something that I think even Webb will be able to address in any direct way, because the truth is we can't see back to that point. There is essentially a wall in time beyond which we cannot see. It's pretty close to the Big Bang, but it's still not.
Why can't we see it? Because we don't have sensitive enough instruments, or there's something in the physics?
It's something in the physics. It's a fundamental limit. It comes out of a branch of physics called quantum mechanics, but there's a fundamental limit shortly after the Big Bang, and it's really shortly. It's like 10 to the negative 40th seconds. It's immediately after the Big Bang, but still there's in principle seems to be an in principle limit beyond which we can't see. So I guess the theologians can talk about that. But from most scientists I know, most astronomers I know are pretty much agnostic on that point.
So to sort of combine those two, Jim also asked the question, will we be able to go back in time and see when the Lord said, "Let there be light"? And that's a religious phrasing. Another way, do you think we'll get a more precise date or determination of how long ago the Big Bang was? Because I know there's a lot of this, it could have been the 5 billion, could have been.
Yeah, I mean, I think we might be able to narrow down the range a little bit, but it's already fairly narrow. 13.38 billion plus or minus several tens of millions of years.
And that there's no expectation that something that's going to come from this new data will knock that around a little bit.
It might tighten. It might do what we call tighten up the error bars a little bit, but it won't. Yeah. We don't expect any dramatic shifts from that number.
Okay. No. Hey, so Katrina says, and this is a very interesting question. What's the time between the collection and the sending of the data from the telescope and when the data is received? Like how long does that whole thing take?
Well, I don't know how long it is between the collection and the sending. I don't know how that works. It's called telemetry. I don't know how the telemetry timing works, but once it's sent, it will probably take 5 seconds to get to the Earth.
Okay.
Something like that.
Does it get is it gathered up and then sent in big batches from a computer?
Yeah, I'm pretty sure it's not continuous. I'm pretty sure that it's sent in batches. That's how I've been accustomed to hearing it done with other similar, Hubble and so forth. I don't think it's sent continuously.
Yeah, that just blows my. I mean, even how that it comes into a satellite, obviously, right? Like it's sending it. It sends that data in what form? What format is that data in?
Radio waves.
Good old-fashioned radio waves.
Good old-fashioned radio waves. Old school.
Hot dog. Old school.
Those things are great. Radio waves are great because they go through everything. They pass through. That they're great.
Well, a fellow, maybe Decterian, Davida Parnell says, "Hi, Paul. Great to see you." So that's just a little freebie for you. Well, and then Davita's saying, "I'm playing the guitar now," so fair enough. Shelley Rasmussen Pagitt said, is about to do a video series on infrared emotions. I don't know what's going on there. All right, Dave Alexander says, I heard in a rural bar, they say that the Webb thing is up there to act like a telescope, but to me, it looks like a big cell phone antenna and the damn communists to talk to the aliens. I don't think he's kidding. I think there's people who are really concerned about all this.
Oh, God knows it's true. God knows they're out there. That's what NASA's been working on for the last 25 years right there.
And the vaccine chips and everything are all tied into the telescope.
Chips,
is that
yeah.
Hey, what were they doing sending this thing up on Christmas Day? I mean, was that like a genius move and like a little Christmas gift, at least, to North Americans?
I think it's a little bit of NASA PR for sure.
Little wink and a nudge.
Yeah. They didn't have to do it on Christmas Day, but I think they realized they could.
Like all the scientists aren't celebrating Christmas anyway, that kind of thing. Is that
all I thought about was all the scientists' kids sitting around the house without mom and dad,
Well, for us, it was like look for stockings and then watch the replay that my daughter had us all watch, who's 32 years old, had us all watch, the launch of the thing. So it was very Christmas miracle to us.
So your daughter's a space nerd, is she?
Super space nerd. And our little grandson is being fully indoctrinated into all of that with astronaut stuff and spacey stars and all of it.
Wonder where they got that from.
A very confused member of the family that is trying to wrap his brain around this and felt like he should have paid attention in college. Well, Paul, this is thanks. This is super helpful. We were going to try to talk about some other things, but of course, I just get my brain stuck on this, and I'm going to keep ruminating on these ideas and trying to understand how we are looking further in the past to see waves that are expanding all directions and coming toward us. Wow, that's
what a weird universe we live in, huh?
Yeah, Monday we're going to talk about hallucinogenics here on the podcast, so these two are going to go well together.
Very, very fine line. Very fine line. Well, here's to many happy hours of thinking about that stuff.
Okay. Do you have another minute?
Yeah.
No, you have to run. What are you most excited about this telescope? Is there something that for you and what you've done in the past and the work you're doing in the future that you think, boy, this is what's got my interest cranking?
Not so much related to what I've done in the past, but really the two things that I'm most fascinated with are I want to, this expansion we've been talking about of the universe, discovered about 20 years ago that it's speeding up. It's not slowing down. And for decades before that discovery, everybody assumed it was slowing down for reasons I won't get into. But everybody basically assumed, based on simple assumptions, that it'd be slowing down, but it's speeding up. And I'd like to know, I'd love to see Webb help us make inroads into answering the question as to why that is, why it is that it's speeding up, because we don't know.
What information came 20, 25 years ago or was
basically
that changed that?
There were two studies and they were done independently, which helps. There were two big groups of researchers working independently, looking at things called type 2 supernovas. Type 1 supernovas. And without getting into the weeds here, essentially what we learned from these studies, they both learned the same thing, which is that over time, the rate at which the universe is expanding has increased. It was assumed before that because of gravity, which is always attractive, that it would be slowing down.
Yeah, is that entropy or something like that?
All matter, all galaxies would be attracting all other galaxies all the time, and that would tend to put the brakes on it. But it's going in the opposite direction. It's going faster and faster and faster all the time. We don't know why.
And when it's
we call it dark energy, but nobody knows what the hell it is.
There we go. Yeah, it's this force that we don't know, so we just say it's still the light has not been shined on it yet, so it's still in the dark.
We don't, but giving it a name doesn't mean we know what it is.
Dark chocolate. So when the universe is expanding still, is it now expanding into space that is it like the Big Bang where it's creating the space?
There's more and more space every second.
Okay.
There's more space every second.
All right.
And not only that, but every second there's more and more and more space because it's speeding up.
And there's more space faster than there was yesterday.
That's what I meant to say. Yes, there's more space was created in the last 24 hours than was created in the previous 24 hours. There you go.
But no matter is being created, like right in the cosmos. So one of the things I was taught years ago watching a great course DVD was that there's no increase in the amount of matter. Everything in our universe is transforming and exchanging from mass and energy and so on. There's no gaining or losing of anything, but space is expanding and expanding faster, but that's not adding no new stuff is being made. Is that
right? So the universe is getting less dense.
Say that again.
The universe is getting less dense. It's getting thinner and thinner.
What?
And there's nothing we can do about it except for watch it. Just be witnesses. That's it.
I'm going to go lay down after this.
Yeah.
Thank you, my friend. We'll see you in.
You're welcome.
Hey, and thanks everybody for being a part of all of this.
It's a lot of fun.
To all the bots on YouTube. Thank you for all your nonsense that you've been putting in here. Ryan, Julio, Davida, Katrina, Jim, Kevin, all of you. Thanks so much for Tim for being conversation partners with us in this. Share this if you would. Hey, go over to our YouTube channel. Please, all of you go over there and just subscribe to the Vote Common Good YouTube channel. We're trying to do some things over there and we need to get some more subscribers. So if you do that, it really helps us a lot. Do it with every email account you have. Just re-log in and do your, however you get into YouTube and just subscribe to that thing. It really help us. All right, Paul. Thanks, my friend.
You're welcome. It was a lot of fun.
Talk to you later.
See you next time.
Bye.
Bye.